you filthy swine! Get in here, have a seat, sit on those trotters and listen. One thing I wanted to figure on is a more rudimentary description of quantum computers and perhaps to dispel some of my preconceptions, maybe yours as well. Let's see what this says. So I have this article here on quantummagazine.org, written by Scott Aronson. What makes quantum computing so hard to explain? To understand what quantum computers can do and what they can't, avoid falling into overly simplistic explanations. It's a good idea. Quantum computers, you might have heard, are magical uber machines that will soon cure cancer and global warming by trying all possible answers in different parallel universes. For 15 years on my blog and elsewhere, I've railed against this cartoonish vision, trying to explain what I see as a subtler but ironically even more fascinating truth. I approach this as a public service and almost my moral duty as a quantum computing researcher. Alas, the work feels Sisyphean. The cringeworthy hype about quantum computers has only increased over the years as corporations and governments have invested billions and as the technology has progressed to programmable 50-qubit devices that, on certain contrived benchmarks, really can give the world's biggest supercomputers a run for their money. And just as in cryptocurrency, machine learning and other trendy fields, with money have come hucksters. In reflective moments, though, I get it. The reality is that even if you removed all the bad incentives and the greed, quantum computing would still be hard to explain briefly and honestly without math. As the quantum computing pioneer Richard Feynman once said about the quantum electrodynamics work that won him the Nobel Prize, if it were possible to describe it in a few sentences, it wouldn't have been worth a Nobel Prize. Well, there you go. I suppose, yeah, like E equals mc squared may be very simple, but you need a whole lot of explanation to unpack what that means. Not that that stopped people from trying. Ever since Peter Shaw discovered in 1994 that a quantum computer could break most of the encryption that protects transactions on the internet, excitement about the technology has been driven by more than just intellectual curiosity. Indeed, developments in the field typically get covered as business or technology stories rather than science ones. That would be fine if a business or technology reporter could truthfully tell readers, look, there's this deep quantum stuff under the hood, but all you need to understand is the bottom line. Physicists are on the verge of building faster computers that will revolutionize everything. The trouble is that quantum computers will not revolutionize everything. Yes, they might someday solve a few specific problems in minutes that we think would take longer than the age of the universe and classical computers. But there are many other important problems for which most experts think quantum computers will help only modestly, if at all. Interestingly, physicist Sabine Hossenfelder, I read a statement from her on X a few weeks or months ago that she was not impressed with the potential of quantum computing. Also, while Google and others recently made credible claims that they had achieved contrived quantum speedups, this was only for specific esoteric benchmarks, ones that I helped develop. A quantum computer that's big and reliable enough to outperform classical computers at practical applications like breaking cryptographic codes and simulating chemistry is likely still a long way off. But how could a programmable computer be faster for only some problems? Do we know which ones, and what does a big and reliable quantum computer even mean in this context? To answer these questions, we have to get into the deep stuff. Let's start with quantum mechanics. What could be deeper? The concept of superposition is infamously hard to render in everyday words. I like to think of it as like a fog, a smudge. Think of it as if you just drawn a drawing and the ink is still wet and you smeared your thumb over it. That's, in my mind, the idea of a superposition. All states, as they could be, are in a kind of fog of potential. So not surprisingly, many writers opt for an easy way out. They say that superposition means both at once, so that a quantum bit or qubit is just a bit that could be both 0 or 1 at the same time, while a classical bit can only be one or the other. They go on to say that a quantum computer would achieve its speed by using qubits to try all possible solutions in superposition, that is, at the same time or in parallel. This is what I've come to think of as the fundamental misstep of quantum computing popularization, the one that leads to all the rest. From here, it's just a short hop to quantum computers quickly solving something like the traveling salesman problem by trying all possible answers at once, something almost all experts believe they won't be able to do. The thing is, for a computer to be useful at some point, you need to look at it and read an output. If you look at an equal superposition of all possible answers, the rules of quantum mechanics say you'll just see and read a random answer. And if that's all you wanted, you could have picked one yourself. What a superposition really means is complex linear combination. Here we mean complex, not in the sense of complicated, but in the sense of a real plus an imaginary number. While linear combination means we add together different multiples of states. So a qubit is a bit that has a complex number called an amplitude attached to the possibility that it's 0 and a different amplitude attached to the possibility that it's 1. These amplitudes are closely related to probabilities, in that the further some amplitude is from 0, the larger the chance of seeing that outcome. More precisely, the probability equals the distance squared. Getting a bit blurry there in my mind, but amplitudes are not probabilities. They follow different rules. For example, if some contributions to an amplitude are positive and others are negative, then the contributions can interfere destructively and cancel each other out, so that the amplitude is 0 and the corresponding outcome is never observed. Likewise, they can interfere constructively and increase the likelihood of a given outcome. The goal in devising an algorithm for a quantum computer is to choreograph a pattern of constructive and destructive interference so that for each wrong answer, the contribution to its amplitude cancel each other out. Whereas for the right answer, the contributions reinforce each other. If and only if you can arrange that, you'll see the right answer with a large probability when you look. The tricky part is to do this without knowing the answer in advance and faster than you can do with a classical computer. Blimey. This is a bit of a mind bender, yeah. If we're talking about amplitudes, I'm thinking about if you imagine a straight line which represents 0, above that line is positive numbers, below that line is negative numbers, and they're saying the higher up the amplitude, the more probable that is true. So instead of having a 0 or a 1 in a transistor, it's either on or off. You have a higher probability of it being on or a higher probability of it being off, and maybe those two things cancel out to a certain extent. 27 years ago, Shaw showed how to do all this for the problem of factoring integers, which breaks the widely used cryptographic codes underlining much of online commerce. We now know how to do it for some other problems too, but only by exploiting the special mathematical structures in those problems. It's not just a matter of trying all possible answers at once. Compounding the difficulty is that if you want to talk honestly about quantum computing, then you also need the conceptual vocabulary of theoretical computer science. I'm often asked how many times faster a quantum computer will be than today's computers. 1,000,000 times, 1,000,000,000? This question misses the point of quantum computers, which is to achieve better scaling behavior or running time as a function of n, the number of bits of input data. This could mean taking a problem where the best classical algorithm needs a number of steps that grows exponentially with n and solving it using the number of steps that grows only as n squared. In such cases, for small n, solving the problem with a quantum computer will actually be slower and more expensive than solving it classically, as n grows at the quantum speed up first appears and then eventually comes to dominate. Okay, so the more steps required in the calculation of an algorithm, the more beneficial the quantum computer is. He's kind of railed against the idea that it's trying all possible answers. Still trying to understand this. But how can we know there's no classical shortcut, a conventional algorithm that would have a similar scaling behavior to the quantum algorithms? Though typically ignored in popular accounts, this question is central to quantum algorithms research, where often the difficulty is not so much proving that a quantum computer can do something quickly, but convincingly arguing that a classical computer can't. Alas, it turns out to be staggeringly hard to prove that problems are hard, as illustrated by the famous P versus NP problem, I don't know what that is, which asks roughly whether every problem with quickly checkable solutions can also be quickly solved. This is not just an academic issue as a matter of dotting I's. Over the past few decades, conjectured quantum speedups have repeatedly gone away when classical algorithms were found with similar performance. Note that after explaining all of this, I still haven't said a word about the practical difficulty of building quantum computers. The problem, in a word, is decoherence, which means unwanted interaction between a quantum computer and its environment. Nearby electrical fields, warm objects, and other things that can record information about the qubits. This can result in premature measurement of the qubits, which collapses them down to classical bits that are either definitively 0 or definitively 1. The only known solution to this problem is quantum error correction, a scheme proposed in the mid-1990s that cleverly encodes every qubit of the quantum computation into the collective state of dozens or even thousands of physical qubits. But researchers are only now starting to make such error correction work in the real world, and actually putting it to use will take much longer. When you read about the last experiment with 50 to 60 physical qubits, it's important to understand that the qubits aren't error corrected. Until they are, we don't expect to be able to scale beyond a few hundred qubits. Once someone understands these concepts, I'd say they're ready to start reading, or possibly even writing an article on the latest claimed advance in quantum computing. They'll know which questions to ask in the constant struggle to dismiss reality from hype. Understanding the stuff really is possible. After all, it isn't rocket science, it's just quantum computing. Okay, Scott Aronson, thank you for that. You haven't really enlightened me much, though. You've given more of a mechanical understanding of quantum computing, which is fine. It's interesting. I think between nerds and non-nerds, if you don't understand something, you still wade in and try and figure it out. Whereas non-nerds probably go, hold on there, that's a load of nonsense. I'm going to go have a cheeseburger and do something constructive. I'm still none the wiser about exactly how these things are working, although I understand the fact that you can have these probabilities cancelling each other out. I get what's kind of going there on a simple level. I get that these quantum computers need to have zero interference from background sources, heat or whatever, to try and isolate these quantum effects. But I still don't understand why visualizing what's going on here as being calculated in multiple dimensions or whatever, why is that not helpful to understanding what's going on here? I know you're talking about amplitudes of probability and whatnot, but I want to know a little bit more about what's going on behind the scenes, because my impression is that multiple effects occur from singular causes. So my bias is that these quantum computers are exploring all effects from a cause and somehow surfacing one select effect, one select answer. And I don't understand how this description of positive and negative amplitudes results in the correct answer coming out. I'd like to know more about that, because that's just kind of breaking my brain at the moment. How do you get the right answer to surface out of that superposition, that blur for possible answers? I don't know. But there we go. Make sure you like this stream. It's helpful. It's encouraging. I like it. Please like me. If you don't like me, that's fine. But anyway, that is it for now. I have nothing else to say except Pigwig out.
Oink, oinkity, snort, schnuffle, schnuffle, squee, oink, oink, wee, squeal, snort, snort, oinkity, squee. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Snort, snuffle, oink, squee, squeal, wee, snort, oinky, oinkity, oink, oink, snuffle, wee, squee, snort, oink, squeal. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Oink, oinkity, snort, snuffle, snuffle, squee, oinkity, oink, oink, snuffle, wee, squee, snort, oink, squeal. Oink, 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 squee, squee, wee, 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 snuffle, snort, squeal, squeal, oinky, oink, snort, snort, squee, oink, 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 wee, 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 oh. Squeal, squeal. Snort, shuffle, oink, re, squeal, re, snort. snuffle, squeal, snort, oink, squeal. Oink, 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 goody, squeal, squeal, re, snuffle, snort, squeal, squeal, oinky, oink, snort, squeal, oink, 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 re, squeal, squeal, snort, snuffle, oink.